Hey folks, welcome back. We've got another data material to go through, so let's get started. This is section 2.3, is the span of a set of vectors. We're going to start with the definition. A system is homogeneous if the constant part of the system is equal to the zero vector. All of the vectors are zero. All homogeneous systems have at least one solution because we can always plug in zero for the inputs and get an answer. Let me show you an example real quick. So just making up an example, if I have x plus 321y minus 47z equals 0, and 2x plus 65y minus 8z equals 0, and 9721x plus 11y minus 185z equals 0. I don't have to row reduce this to know for a fact that x equals 0, y equals 0, and z equals 0 is a solution, because 0 plus 0 plus 0 equals 0 in every case. So all homogeneous systems have a solution, and we call that solution the trivial solution because, well, it's trivial. We don't have to do any work to find it. I can just look at the system and say, oh, it's homogeneous. I know 0, 0, 0 works. It might have more than one solution, but in order to have more than one solution, it must contain a free variable. So let's show that the zero vector is the only solution to this homogeneous system. That means this system cannot contain a free variable. Well, we can do this by row reducing, and this is just one step. I need to change this entry to a 0, so I'm going to take row 2 minus 2 times row 1, and that's going to give me 0. 3 minus a negative 4 is going to be 7, 0, 1, negative 2, 0 in the top row. This is in echelon form, and I have a leading entry in the first column, so x is not free, so x is basic. And I have an entry in the second column, a leading entry in the second column, so y is also basic. So neither x nor y is free, and therefore we don't have an infinite number of solutions, we just have one solution, and we can see that if 7y is equal to 0, y is 0, and then when we substitute up here we get x equals 0. So x equals 0, y equals 0 is the only solution. All right, let's move on. So suppose we have a set of vectors. We say that the span of that set of vectors is the set of all of the possible vectors which are linear combinations of vectors in V. So any combination of weights times these vectors. And the weights might be 0 because we might not be using all of the vectors. That's okay. Any vector that we can build using these starting blocks is a vector that's an entire set called a span. So a single vector that's a linear combination is called a linear combination. But the set of all of the vectors that are linear combinations is called a span. So this is a very large set, probably infinite. Large set containing vectors which are linear combinations. Of V. If that set is so large that it contains every single vector in Rn, it might contain all the vectors. And if it does, if it contains every vector, we say that the set V spans Rn. Or we might say that it is a spanning set for Rn. It's just a different way of saying that. So let's try some examples. Let's see if we can make this work, okay? All right. So my building blocks are 4, 3, and 2, 1. Can we build the vector 5, 3 using these vectors? So that's saying, does there exist weights so that if I weight the first vector and I weight the second vector, that combination is 5, 3. That's what this is asking is, can I build this vector? Will this vector be one of the vectors that's in the span? That means it would be a linear combination. But this is just saying that 4a plus 2b is equal to 5, and 3a plus b is equal to 3. But we can solve this by row reduction. 4, 2, 5, 3, 1, 3. Oh, let's see. We want to get rid of this 3, so let's do 4 times row 2 minus 3 times row 1. So that gives me 4, 2, 5 in the top row. 12 minus 12 is 0. 4 minus 6 is negative 2. 12 minus 15 is negative 3. This is an echelon form. Now the question is not asking how to find the linear combination. It's not asking what the values of A and B are. It's just asking for a yes or no question. Is this vector in span V? We just want to determine if it is. Well, the answer is yes. This vector is in a span because for this not to be solvable, I would have to have a leading entry in the last column. There is no leading entry in the last column. So this is solvable. And so the answer to this question, excuse me, there you go, my pen just wasn't working right for a moment, is yes. But we could go on a little bit further and actually find AB. So the second equation says that negative 2b is equal to negative 3. And that tells me that b is equal to 3 halves. And then the first equation is going to say that 4a plus 2 times 3 halves is equal to 5. Well, 2 times 3 halves is 3, so 4a plus 3 is equal to 5. So 4a is equal to 2, and so a is equal to 1 half. So we could actually solve the system, but that's not actually what the question asked for. That's more work than we needed to do. Okay? Well, why is every vector in span V? We just tested this vector here. Why is it true that every vector is in span V? Well, let's go back and look at the system of equations we had. we had started with 4, 2, 3, 1. And in our special case, we had a 5 and a 3 here. But this doesn't really matter what these values are. When we row reduced it, we ended up with 4, 2, x, 0, negative 2, and something else. Which we could work out what that was. I'll go ahead and do that. It'll be 4y minus 3x. There we go. We did this for 5, 3, but we could do this for any variable, or any set of variables, and we always get leading entries in the left side of the matrix and no leading entries in the right side of the matrix. And so there's nothing special about the 5 and the 3. Every single vector is going to be in span V. And so we have an example now of a set of vectors that spans R2. So 4, 3, and 2, 1 spans the set R2. So let's try another example. Show that this vector is not in this span. So that means we're looking for a linear combination of these vectors that adds up to 5, 2. Well, if we row reduce this, it's going to take, we want to get rid of this 1. So 2 times row 2 plus row 1 will give me 0, 0, and 9. And now we do have a leading entry in the bottom row. This is saying that 0 plus 0 equals 9. Leading entry is in the augmented column. And that tells me that there is no solution. And since there is no solution, this vector is not in this span. And so the set negative 2, 1, 8, negative 4 does not span the set R2, because here's a vector that's in R2 that's not included. To span R2, every vector has to be included, and we just found one that isn't. All right. So write an equation for the span of these two vectors, and then describe the span geometrically. Well, the equation is actually really easy to write. The equation is that the span contains every single vector that's a linear combination of u and v. Well, that would just be some parameter s times 160 and some other parameter t times 961. So we've used s and t as parameters before. We just take all of the multiples of 160 and all of the multiples of 961, and we add them together, and we get some vector x, y, z that way. And so that's the equation. We wanted to describe what this span looks like. Well, let's see, 160 is a vector that travels 1 unit in the x direction and 6 units in the y direction. That's the vector u. And then 961 is a vector that travels, this is going to go off the edge of the screen, I think, 3, 4, 5, 6, 7, 8, 9, maybe just barely fits. 9, 6, negative 1 is going to be down here, because it's going to be actually below this intersection. And that's going to be the vector v. Those what the two vectors look like individually. But when we talk about spanning, that means I could take any multiple of 160, which means I can take 2 times this vector, or 3 times this vector, or 1/2 times this vector, or -1 times this vector. That the s in front of the 160 means I could be anywhere along this line. And then the t in front of the 961 says that from whichever point I end up on this line, I can move any amount I want in this direction. I can go to this point on the first line, and then move in this direction for a length equal to v, or a length equal to -v, or a length equal to half of v. If I pick t equal to 1/2, I can pick any value for t and then move in this direction. That should be -1. I don't know why I left off the -1. Should have been -1 all along. But if I could travel, starting at the origin, any direction in the u, and then change directions, and then travel any direction in the v direction, then my span is an entire plane that contains the vectors u and v. So the geometric description is a plane containing u and v. All right. So let's move on for a second. We would like to look at the question, when does a set of vectors span Rn? Now if we scroll back a little bit, we'll see that this vector, that these two vectors did span Rn, and these two vectors down here did not span Rn. When does this set of vectors span Rn? Well, these two statements mean exactly the same thing. To say that a set of vectors spans Rn means that every single vector in Rn is a linear combination of these vectors. Well, for every vector to be a linear combination, it means that if I put these vectors into a matrix, so the first vector is some column, and then the second vector is the next column, and then the third vector is the next column, and so on and so forth. Try this again. And then I augment that matrix with the vector b. This must have a solution. Well, if that must have a solution, then this entry in B cannot be a leading entry. And that must mean that we have a leading entry before we get here. That this row has a leading entry, but it's not here. And then this entry can't be a leading entry. But that means that this row has to have a leading entry before we get to B. And then this can't be a leading entry, and it means that the next row must have a leading entry before we get to B. And so if every row has to have a leading entry before we get to B, that means that every row has a leading entry on the coefficient side of the matrix and not the augmented side. That means there can never be a leading entry in the augmented column, and so every row must have a leading entry before the augmented column. And this gives us ... the theorem that's on the next slide. This is proposition 2.3.6 in the book. If we have a set of vectors and we want to test whether that set of vectors spans Rn, well, the span of these vectors is Rn if and only if the matrix has a leading entry in every row. So if the original matrix A and not the augmented part has a leading entry in every row. And so now we have a test to know when a set of vectors spans Rn. So let's try a couple of examples. We know that the span of two vectors forms a plane. Let's find an equation for the plane that contains these 3 points. So my points are 1, 0, 2, so that's 1 unit in the x direction, and 2 units in the z direction. So the origin, this point, and then the point -1, 1, -2, so that's 1 backwards in the x direction, 1 forwards in the y direction, and then 2 down in the z direction, so that's going to be down here somewhere. And I want to find the plane that contains these 3 points. Well, this is easy because we're starting the origin. This is the vector 1, 0, 2, and this is the vector -1, 1, -2. And so the equation is that xyz is any weight times 1, 0, 2 plus any weight times -1, 1, -2. If the origin is included in the plane, this is super easy. It's just use these to convert these points into vectors and take their span. Ta-da! So what happens if the plane doesn't contain the origin? So let's look at the next example. So this time we want to find an equation for the plane that it contains the points 3, 1, 2, so 3 in the x direction, 1 in the y direction, and then 2 units up from there. 4, 3, 8, so 4 units in the x direction, 3 units in the y direction, and then 8 units up from there. 1, 2, 3, 4, 5, 6, 7, 8. It's got to be way up there. And then 6, 2, 7, and then 7 units up in the z direction. And so we want to find this plane up here that doesn't contain the origin. So here's what we're going to do. We're going to temporarily shift the plane so it does go through the origin. So we're going to pick one of these points, pick any point to shift by. So I'm going to pick 3, 1, 2, and we're going to shift everything down by 3, 1, 2. So this converts to the origin. I'm going to subtract 3, 1, 2, and that gives me the origin. Then 4, 3, 8, if I subtract 3, 1, 2, I now have 1, 2, 6. And then 6, 2, 7, if I subtract 3, 1, 2, I get 3, 1, 5. So what we did is we took the plane that we're looking for, we shifted it down by 3, 1, 2. Now it goes to the origin. And we know that this shifted plane is xyz is equal to some vector s times 1, 2, 6, not a vector, sorry, some scalar s, some weight s, plus t times 3, 1, 5. And so now we have to shift this equation back up by 3, 1, 2. And so the equation for the original plane is xyz is equal to 3, 1, 2 plus s times 1, 2, 6 plus 3, 1, 5, t times 3, 1, 5. We take the points, we shift them down so that the plane goes through the origin. We write the span of the two vectors that we have, and then we shift the equation back up by adding this vector onto the equation we found before. Now there's more than one correct answer because we could have picked any of these 3 points to shift by, but it doesn't matter. All of those equations are correct and all of them are equivalent to each other. Have a fantastic weekend. See you for the next video. Take care.